Welcome to RF transceiver design course. We are discussing the power amplifier design and we are on module 9. So, regarding power amplifier general consideration we already have seen. Now, we will go for the classification of the power amplifiers. Now, classification of power amplifier mostly done based on how the transistor or MOSFET is conducting, because the amount of conduction that happens in the transistor, that much uh, efficiency will be degraded. So, based on the how we are conducting the transistor and how much power that is delivered to the load, power amplifier has been classified. So, the first classification is a class A amplifier. So, in class A power amplifier, what will happen that this MOSFET or any transistor will remain in saturation or active region for entire cycle of the input. So, if this is if we try to consider this complete RLC network as a lossless matching network, where the supply is coming from VDD, and if we try to plot IDS and VDS, IDS is given by this green curve and VDS is given by this red curve. So, we can write a drain voltage VDS because there is a VDD, which is a supply voltage through the inductor, plus Vp sin omega naught t. So, that is a sinusoidal output that we are getting with the peak voltage Vp. So, here peak voltage is also important in considering the efficiency of the power amplifier. Now, given the load resistance RL, we have a RL which is a 50 ohm. The drain current we can write IDS equal to IDC plus DC current plus Vp by RL sin omega naught t. So, if we assume the lossless matching network, so this matching network which we are designing to transform the impedance which we are looking from this side to 50 ohm, if we consider it as a lossless, the efficiency we can write P out by P in. So, P out by P in. So, if we consider the P out and relation of RMS Vrms voltage with the V peak to peak voltage, that P out is given by Vp square by 2 RL divided by the input power which is coming from the supply voltage, that is IDC, total current IDC into VDD. Now, if we want to go for the maximum efficiency which is given by Vp square by 2 RL, the IDC current we can write Vp by RL into VDD. So, RL will be cancelled out here and we will get Vp, one of the Vp will also be cancelled out. So, Vp by 2 VDD. Now, here the important point is how your voltage swing at the output, it is at what level. If Vp voltage swing is a maximum equal to VDD, then this class A amplifier can reach a 50% efficiency. So, based on this Vp, we can have a 3 kind of efficiency for class A amplifier. So, that is divided in 3 part, efficiency in different scaling scenario. So, the first is the supply voltage and bias current remain at a level necessary for full output power, means supply voltage and bias current remain at the levels necessary for full output power, and only the input signal swing is reduced. So, if we consider only the input signal swing which is changing, then we as the input signal swing will change, our Vp is also changing. So, we can write a Vp square by 2 RL, that is output power divided by the DC power VDD square by RL. So, we can write equal to Vp square by 2 VDD square. So, this is the efficiency 1. So, if we plot this efficiency 1 with respect to the voltage swing which is starting from 0 to VDD. So, here Vp is a voltage swing and this is a efficiency. So, this if we consider input swing as a scaling parameter, then efficiency 1 has a behavior which looks like this, because it has a square behavior, that is Vp square by 2 VDD square. Now, the second scenario is if the supply voltage remains unchanged, means we are keeping supply voltage fixed, but the bias current is reduced in proportion to the output voltage swing. So, it is the same equation if that we have seen, if this bias current is changing with the output voltage swing Vp, then we can write a Vp by 2 VDD. So, this efficiency 2, what will happen, that Vp, as Vp is changing, your efficiency is also linearly changing. So, this is a linear function of the Vp, how it is changing. And if we have a both supply voltage and bias current which are reduced in proportional to the output voltage swing. So, in this, which is very important, that you required a supply voltage also varying with the swing, and it is very difficult to design the amplifier in which you need to scale the supply voltage, then only it will reach the 50% efficiency. So, which is a constant, means if you want a constant efficiency for class A amplifier, then your supply voltage also should change with the swing. So, this is a 3 scenario that is important to understand based on the how the scaling of the input swing or the bias current or supply voltage and the current scaling is happening. So, while designing, we need to make sure that we have a sufficient voltage swing in this class A amplifier. Class A amplifier has one of the advantage that it is a linear and because of its linearity, it is one of the choice in the in using the in power amplifier design. So, this is one of the widely used class A amplifier, power amplifier, because of its linearity. However, the efficiency is not good. So, in order to have a better efficiency, there are other class, that is a class B power amplifier. So, here that this LCM means LC matching, that is same whatever is drawn here, it is mentioned as LC matching, and this is input that is supplied, and we have IDS current and VDS voltage. Now, here what is happening, that instead of making this transistor on the way we have done in class A amplifier for entire cycle, if we keep only class B amplifier on in the positive cycle. So, if we try to make this transistor on only in positive cycle, only the IDS current will flow, and then there is a, due to the matching, you will get a VDS voltage which is a sinusoidal with the peak voltage Vp. So, IDS current we can write in terms of IDS equal to Ip by pi plus Ip by 2 sin omega naught t, and it will go on. We can write this only the positive cycle. Here, when the fundamental component of the current reaches its peak Ip by 2, so this is fundamental component sin omega naught t. So, the total current saying from the load is Vp by RL, that is Vp by RL, assuming the peak swing of this amplifier is Vp at the drain. So, we can write Ip by 2 which is equal to Vp by RL. So, efficiency is equal to P out by P in. So, output power is given by Vp square by 2 RL as we have discussed in the class A amplifier, and the input power is given by Ip by pi. So, this is a DC term, DC current Ip by pi into VDD. So, this pi will go up, and we will have a pi by 4 into Vp by Vdd. So, that here Ip, this Ip is replaced with the 2 Vp by RL. So, we can write it down, Vp Vp square by 2 RL divided by Ip by pi. So, 1 by pi into 2 Vp by RL into Vdd. So, one of the Vp will be cancelled out, then RL will be cancelled out. We will have a pi by 4, this pi will go up, pi by 4 Vp by Vdd. And if our peak to peak voltage Vp will reach to the Vdd, then we will have a efficiency which is a pi by 4. So, we will have a more than 50% efficiency, around greater than 70, if we try to use a class B power amplifier. Now, here what we are doing is we are reducing the conduction of the conducting transistor. So, that conduction is also denoted as a conduction angle. So, as we reduce the conduction angle theta for the transistor which is driving the load, that will reduce the amount of power consumed by the transistor. So, the maximum power will be transferred to the load and efficiency will increase. Now, there is another amplifier, that is a class C amplifier. Now, in class C amplifier, we again further reduce the conduction angle. Instead of only the positive cycle, if we try to reduce the conduction angle only for few cycle, means half of the cycle, then as drawn in this figure, here VGS is drawn and there is IDS current. So, it is conducting only for this cycle. We need to bias the transistor such that it will conduct only for small amount of period. So, if we here assuming a conduction duration which is a tau less than T by 2, in the previously it was a T by 2 more than this. If it is where T is a 1 cycle, we can see that the device turns on and off at a 2 points, T on by off equal to T by 4 plus or minus tau by 2. We can write a tau which is equal to T cos inverse VTH. So, this VTH threshold voltage by V peak voltage P by pi, where the conduction angle theta which is given by. So, this conduction is happening only in the duration where cos inverse V threshold by Vt, and it is given by pi by T into tau. Now, during the conduction, the drain current IDS is given by Ip into minus cos theta plus sin theta, and here time t is between T on and off. So, only this period. So, for T is equal to, if we consider T is equal to T on and off, which is this, IDS is equal to 0 and IDS is equal to Ip by pi. So, for other period it is 0, and if we consider only this much period which is a tau by 2, IDS which is equal to Ip by pi sin theta minus theta cos theta plus theta minus sin 2 theta by 2. This is the fundamental tone sin omega naught c. So, to get the swing Vp at the RL during the conduction, we must have a Ip which is equal to pi into Vp by RL divided by theta minus sin 2 theta. So, this is a as we have seen in the class B, this is fundamental tone we need to consider. So, Ip which is given by pi into Vp by RL by theta minus sin 2 theta by 2, because that current is only the IDS is only provided during this period and it is divided by this term. Now we write a P out by P in, P out nothing but Vp square by 2 RL, it is same, and P in Ip by pi into Ip by pi into this sin theta minus theta cos theta into VDD, that is this DC term Ip by pi sin theta minus theta cos theta VDD, and now we can write a Vp by RL, we replace Ip with this Ip. So, when we replace Ip with this Ip, this pi will be cancelled out and this theta minus sin 2 theta term will go up, and this will be down, and this is Vp will be cancelled out, RL will be cancelled out. So, Vp by 2 VDD. Here if Vp is equal to VDD, then this is a efficiency which is depend upon the how much conduction angle theta. Now conduction angle theta is depend upon the V threshold by V peak. So what is at what period of time it is switching on, based on that we can have a efficiency that we can define. So ideally if we try to plot the efficiency versus the angle theta, for a 0 degree we can get a maximum 100% efficiency by using this equation. But we, as this conduction angle will increase, because that will reduce the efficiency. Class B has a 79% efficiency where it is conducting for 180 degree, and class A which is for 360, it is a 50% duty cycle, 50% efficiency. There is a trade off here also has been observed, that if the conduction angle which is approaching to 0, the output power, that P out, will also reducing to the very less. So there is a trade off, that maximum output power that we get and the efficiency that we get versus a theta, which is given in this another plot. So we need to choose the if we want to achieve the higher efficiency, the amount of power, output power will reduce. So while designing we need to consider this also, that what is the output power that we are going to reach for the different conduction angle. Now there is another class in all the class that we have seen, class ABC, which is a widely used class, where the conduction we have defined the conduction, how the conduction is happening. Now in another high efficiency power amplifiers, or what we try to do is we try to use two features. One is we try to modulate the impedance for different means different harmonics. We try to modulate the impedance with the different harmonics, and we also try to make the, instead of using a transistor as a voltage current control voltage device. So where voltage we are applying a voltage and its output current is changing, that instead of that we try to use a MOSFET as a switch. So if we try to use a MOSFET as a switch, then amount of time that transistor is on will be reduced and the maximum power will be transferred. Now in order to, when there is a digital switching we are doing, we need to make sure that our output means the output waveform is should be shaped properly, so that the sinusoidal output will you will get. So in that case the impedance matching is very important. So if we have a class A stage, let us say, and if we suppose the matching network is designed such that its input impedance is low at the fundamental and high at the second harmonics. So, what we try to do is we try to make a the fundamental harmonics which is passed. So, when there is a fundamental harmonics will come, at that time the impedance is a low, that Z1 impedance is low, and for other harmonics the impedance will high. So, we need to properly design this impedance matching network. So, there is a sine omega naught t, if for a second harmonic to omega naught plus 90, the if we have a 0.3 sine to omega naught plus 90, and then if we have a combination of these two signal, it will something look like this. So, it is most likely the what we are trying to do is uh, trying to make it more digital instead of a analog, the way we have done in the class A amplifier. So, here the average power consumed by the output transistor decreases and the efficiency increases. That is why this kind of methods will be used to improve the efficiency of the power amplifier. There is another class which is defined as a class D. D means digital also, where if we try to this is a basic inverter configuration where during the positive cycle it will charge and negative it will discharge. So, it will mostly VDSN means IDSN will look like this, and VDSN is more like a switch. So, and this is a inverter. Now, this if we try to redraw this as a switch where it is on and it is first charging and discharging behavior, we can write a load voltage peak current V load equal to 2 by pi, because we are considering the switching and we have seen that when we are considering the square wave, the DC is a 2 by pi. So, that is V load 2 by pi VDD into RL, that is total voltage VDD into RL divided by what we are doing is the amount of voltage that is coming at this node. So, the if we use a voltage division rule, that RL divided by RL plus R switch plus RL will give the load voltage V load, and current I load which is given by 2 by pi VDD divided by the total resistance R switch RL by plus RL, small rl plus RL. So, to efficiency we can write the P out by P in equal to V load into I load by 2 IDC into VDD. So, if we replace V load and I load in this equation, what we will get RL by RL plus R switch. So, in this your efficiency is depend upon the load resistance and the inductor quality factor and the switch resistance R switch. So, this if we consider this RL which is very high in this case, and if we try to reduce the R switch resistance, then this term RL divided by RL, and it will be efficiency is equal to 1. So, there is a possibility to get more than 100 percentage, means more than 90 percentage efficiency or around 100% efficiency if we design this switch with a low resistance and if we have a better matching network. We can also have a differential amplifier configuration which looks like here, where this is a tuned circuit for impedance matching, and this is how we can make this more look like a square wave. Only for positive signal and negative signal, the differential signal will be applied to the tuned circuit. So, this is called a class D amplifier, power amplifier. Then there is a class E amplifier. Now what we need to do is, in class E stage we need to revisit the output stage with a switching transistor. So in class E also what we do is, we use a uh, transistor as a switch, the way we have used in the class D. So in class E stage are nonlinear amplifiers that achieves efficiency which is approaching 100 percentage while delivering the full power, and it has a very remarkable advantage over a class C circuits. In switching power amplifier, it achieves the high efficiency if this M1 transistor which is shown here uh, sustain a small voltage when it carries a current, means it should have a very small voltage when it so it is like a complete short, and M1 carries a small current when it is finite voltage, means when it is on it does not, it should pass the current, means it is kind of ideal switch, and when it is off it should have a very minimal, means it should not have any current, and the transition time between the on and off states are minimized. So if we have a ideal switch kind of configuration, then we can have a better efficiency. Though there is a, as shown in this figure, there is a certain on resistance, and when it is off, if there is some leakage current, so that we cannot, because of that we cannot achieve the 100% efficiency, but it will be close to the good efficiency that we want. So in class A amplifier, the main challenge of a class D PA that we have discussed is to minimize the voltage across the switch when it is carrying the current, and the current through it when there exists a voltage across it. So making it a more ideal switch, that was a one challenge when we have seen the class D. Now this condition, what is called a fast switching, which is very difficult at a high frequency, and if the switch voltage and current which is, if it will overlap, they generally do in practice due to the finite rise and fall time. We cannot have a ideal uh, digital voltage and ideal switch, and the efficiency degradation may substantially happen, and this can be avoided by proper design of a matching network. So we need to design the matching network properly, and which adds enough degree of freedom to ensure that there is no appreciable time duration that voltage and current simultaneously exist. So that is that way we can improve the efficiency. Now there is a class F power amplifier. So in class F power amplifier, what has to be done? We will use the M1 transistor as a switch only, but the way we have improved the efficiency in class A amplifier by making the input impedance looks low for the fundamental frequency and high for the other harmonics, it is improving the efficiency. So same thing, if we try to make this impedance Z1, if this try to make this input impedance low for fundamental tone and high for other harmonics, then we can achieve the higher efficiency in class F amplifier. So in a generic switching state, the load network provides a high termination impedance at the second or third harmonics, and the voltage waveform across the switch exhibit a sharper edges than a sinusoid, thereby reducing the power loss in the transistor, and this kind of circuit is called a class F stage, and where Vx which is drawn instead of square, it looks like a sinusoidal waveform. So this is what the all the efficiency that means this is about the efficiency of power amplifiers. So we have seen all the different class of the power amplifier, class A, B, C, D, E, F, and class ABC, which is defined based on the conduction angle. Class D, E, F is how digitally we switch and reduce the amount of power that is consumed by the transistor, and it improves the efficiency. In all these cases, impedance matching network is very important for designing, and we have given enough time to design the impedance to understand the impedance matching during the initial lectures. Thank you. We will discuss about the linearity improvement in the next class.